Hello and welcome back. This is AG3 8.2 first video. We're continuing talking about similarity and transformations. I don't know what happened to the other videos, so I had to remake this one, so I apologize. On today's notes, normally I want you to copy every single thing. Today I want you to copy the first page and follow along on pages 2 and 3. The examples, it's a lot, and so I really just want you seeing the examples and moving forward. Our essential question is, when a figure is translated, reflected, rotated, or dilated in the plane, is the image similar to the original figure? So a couple things here. Translated means to move. It slides back and forth. Reflected is like a mirror. It flips. Rotated, it spins, turns on an axis. Dilated, it zooms in or zooms out. The image is our second or ending point. The original figure is always called the pre-image. Okay. So a couple things here, definitions. A dilation in which we zoom in or zoom out, enlarge the figure or reduce the figure. It's going to preserve the shape of the figure but not the original size. So the shape is going to stay the same. We can't go from a triangle to a circle. That is not a transformation. A similarity transformation is when a dilation or composition of rigid motions and dilations. And what happens is we're going to have a zoom in, zoom out, enlargement, reduction. We can slide it and rotate it and flip it. But once we dilate it, we're changing the size but keeping the shape. And this is going to become a similar figure in which it has the same shape but not the same size. So we're just moving figures in and out of the plane. So let's look at an example. We're going to perform a similarity transformation. We are given a graph of triangle ABC with vertices that A is negative 4, 1, B is negative 2, 2, and C is negative 2, 1. And its image after the similarity transformation. So we're starting here, A, B, and C. There is no primes on it, so it's our starting point. Once we move, it's going to become A prime, and then we move again, it's going to become a double prime. So how do we move it? Well, these are our directions. The translation is, first we're going to move it for every x and y value. We're going to add 5 to every x and add 1 to every y. And that's going to give us A prime, B prime, and C prime. Once we get these new points, we're now going to go and multiply each x and y by 2, which is going to increase it, shrink it, or enlarge it. In this case, it's going to enlarge it. So what does that look like? So for A, we have negative 4, in which we are adding 5, and that's going to give us 1. And then we're going to have 1, that's this part right here, plus 1, and that's going to give us a 2. So our A prime now becomes 1, 2. We do that for each part. B prime is going to be negative 2 plus 5. Negative 2 plus 5 gives me 3. And then 2 plus 1 gives me 3 as well. And then C prime is going to be negative 2 plus 5, which is 3. 1 plus 1 gives me 2. But we're not done there. That's just the first move. Now we got to take each one of these points and multiply them by 2. So now we're going to get a double prime, B double prime, and C double prime. And the way we get that is we're going to multiply everything in here by 2. So 1 times 2 is 2. 2 times 2 is 4. 3 times 2 is 6. 3 times 2 is 6 again. And then 3 times 3 is 6. 2 times 2 is 4. So what's happening is we're starting at these points. That's our first triangle. We're coming to our first move, which is here. And then our second move, which is here, our double primes. I think it's easiest to do it in the points, and all you got to do is the math here. However, I think some of us are visual learners, and so we need to see what's going on. So how do I know which one's our starting triangle? I look at the points. A, there's no prime here. Here's A prime, that's our first move. Here, double prime, that's our second one, so I know this is our starting point. And we started off at negative 4, 1, negative 2, 2, and negative 2, 1. And then we added 5 and added 1. And so A prime is 1, comma 2, and that's what we have in our calculations. B prime is 3, 3. That works. C prime is 3, 2. Boom, that's what we had. And then we multiplied each one of these by 2, and then we got 2, 4, A double prime, B double prime is 6, 6, and C double prime is 6, 4. All we're doing is following directions, and we want to see the ending result. So we're going to translation, we're going to add or subtract, and then a dilation, we're going to multiply or divide. And in math terms, we translated, so starting with our blue figure, how do we get to our green? One way we can say is we translated ABC 5 units up. 1, 2, 3, 4. That's 4. 1, 2, 3, 4. Oop, no. Translated 5 units to the right and 1 unit up. My bad. So we went 1, 2, 3, 4, 5 units to the right, 1 unit up. Yep, that's what happened there. And then vertices, we already found the vertices. And then we multiplied by a scale factor of 2. So it's just trying to give you in words what we did in these calculations. So you're following the directions. Whatever it tells you to do in here for our x and y, and it gives you an arrow. This is our new pot. How do we find our new points? This is how we find our new points. What's also going to happen is they're going to give you the starting point, and they're going to ask you, how do you get to the ending point? Describe the similarity transformation that maps trapezoid PQRS to trapezoid WXYZ. So PQRS, and we're going to go to WXYZ. So what do we notice? How do we go from the blue to the green? Well, first of all, this one's going, QR is going down, YX is going up, and then so that means it's flipped like a mirror. And the way we say that is it's a reflection. QR falls from left to right, it goes down. XY goes up, rises from left to right. This is a reflection. It's flipped like a mirror across this black line. And then it gets smaller. And so how does it get smaller? We divide by a number or multiply by a fraction. And so in steps, they went from PQRS. We reflected it across the y-axis, and that's how we got the purple. And so we put that in words, a reflection across the y-axis. And now to shrink it, we're going to start dividing by numbers. And so how do we go from 3, 3 to our x? And so our x is 1, 3. So how do we go from 3, 3, from 3, 3 to 1, 1? Well, we're dividing, and so what number do we divide 3 and 3 by? We divide it by 1, and that's how we get to 1, 1. If we divide 6 by 3, we get 2, and if we divide 3 by 3, we get 1, so 2, 1 should be our next point. 1, 2, 1, there's our next point, perfect. 0 divided by 3 is 0, negative 3 divided by 3 is 1, so 0, negative 1, there it is. And then 6 divided by 3 is 2, and negative 1, 1, 2, negative 1. So what I want you to understand is that we're shrinking by dividing, and the way that I got to 3 was just trial and error. We can divide by 2, we can divide by 3, and we keep on going until we end up at our smaller points. So trapezoid WXYZ appears to be about 1/3 as large as trapezoid PQRS, so that's how we divide by 3. Another way of dividing by 3 is by multiplying by 1/3. And so the directions would be to find our new points is to multiply everything by 1/3 or dividing by 3. So from P prime to P double prime, and that's how we found all our new points. And so the similarity transformation that maps trapezoid PQRS to trapezoid WXYZ is a reflection in the y-axis, and then followed by a dilation of scale factor of 1/3. So if you're not sure how to write that or how to say that, you'd always can ask me. Instead of saying divided by 3, we can say a scale factor of 1/3. What I want you to take away from this is that similarity transformations keep the shape but not the size, and that the transformations are just directions from the pre-image to get to the image. Try the questions and forums. Let me know how you do. If you struggle, look for new videos today.